Hi, welcome back. Dr. P here again, and I'm going to pick up where we left off last time, talking about the hydration or addition of H2O to alkenes. So last time we saw the following additions. We saw, and let me go ahead and draw something, an asymmetric alkene here. So we'll do H2O, H plus, or we can do HgOAc2 and water, followed by NaBH4. And so both of these hydrations are Markovnikov additions. And then the oxymercuration-demercuration is also an anti-stereochemistry. So that was last time. But today, or in this lecture, I want to talk about a different oxidation. Not oxidation, sorry, a different hydration. Hydrations are not oxidations. A different hydration, which is hydroboration-oxidation. The first step will be to react our alkene with a boron compound, and the one we use is BH3.THF, and I'll draw that in just a minute. And then we will go ahead and oxidize that with the with peroxide in the presence of base, and what we end up getting is an anti-Markovnikov for the regiochemistry, and what we call syn stereochemistry. So let's take a closer look at that. First of all, BH3.THF it's a stable form of borane. Borane is BH3, which actually doesn't exist as BH3. It exists as B2H6. And is kind of unstable. And so our BH3.THF is going to be this guy, and we actually have positive formal charge on the oxygen, negative on the boron. Because the oxygen is more electronegative than the boron, really more of the electron density is pulled towards the oxygen. But this is our way of reacting or having a reagent that reacts like BH3, because BH3 is too unstable. And it actually forms B2H6, which has this really funky structure here. Hold on one sec here before I get into the B2H6 structure. And I'll put my question mark and exclamation points here. This is, I know, this looks crazy. These aren't real single bonds, okay? So we don't have two bonds on hydrogen here, but we have this kind of strange, we have the hydrogens that sort of function like bridges between the two borons. So we're not going to worry about this stuff here, so forget I ever wrote that. Instead, we're going to look at what's going on with our borane, which is what we call BH3, when it adds to our alkene. So let's take a look at this mechanism. And again, I'm going to do a partial mechanism here. I won't go through the whole thing. So let's take a look at what's going on. So what we have is we have our alkene, and then we're going to have B, H, H, H. And this is from the BH3.THF, but I'm just going to show this part. And so what, excuse me, what we're going to get here is we're going to get our lone pair, not lone pair, rather our pair of electrons from the double bond adding to the boron. And then at about the same time, we will have our hydrogen as a hydride add to the more substituted. So that will end up giving us, let me put a hydrogen there just so we can see this. We'll have H, and then we will have B, H, H, and we will have an H there. And then subsequent oxidation, and I'm not going to go into the mechanism of this, but subsequent oxidation then replaces the BH2 with an OH. Now, there's a couple of reasons why we have an anti-Markovnikov excuse me. There are a couple of reasons why we have an anti-Markovnikov addition. One is we have some steric considerations. So if I had, let's say I have my H, B, H, H, and then I have my C, double bond C, let's put an H there, an H there, C, H3, H. So we have less steric hindrance at the end that's less substituted. So up here, just having one methyl versus two methyls, there's less steric hindrance. So it's a little easier for the boron to get in close on that side. The other one is an electronic reason. And if we go ahead and look at the transition state, we'll see that what's happening is this carbon-boron bond is forming. The boron-hydrogen bond is breaking, and the carbon-hydrogen bond here is forming. And so what we'll end up with is a partial positive charge on that carbon, because the electrons from that CC bond are going to make the new CB bond. And we'll actually get a partial negative on the boron here, delta minus. So this is our transition state, double dagger there. So in this transition state, whatever does a better job of stabilizing that partial positive charge is going to be, well, more stable, and then the preferred transition state. So here we have a more substituted carbon, which is better at stabilizing that partial positive charge. So this would be a more stable transition state. So we'd say delta plus on more substituted carbon. And this goes back to what I mentioned as the extended Markovnikov rule, which is that in the electrophilic addition of something to an alkene, things add in such a way that you make the most stable intermediate or transition state. So last time we saw the most stable intermediate for either a carbocation or the mercurium ion. And here we're seeing a transition state that's more stable. All right, so that was hydroboration-oxidation. And in the next few lectures, we'll go ahead and take a look at some more additions. I just realized one more thing. This also explains the syn addition, because this guy's adding in from both things at once from one side. So it's not like we have that three-membered ring and then it's being opened from the opposite side, or we make a carbocation and things could add from either side. The hydrogen and the boron add from the same side. So that's something important to remember. This is a syn stereochemistry. We have syn stereochemistry as opposed to the mercuration, demercuration, oxymercuration, demercuration, where we have an anti-stereochemistry. All right, well, until next time, stay safe out there. Bye now.